Okay, today we're going to do two more examples of related rate problems. We did two in the last lecture, and so this one is going to be example number 3. Okay, so let's just read it. A police officer is traveling north at a speed of 30 miles per hour toward an intersection a half a mile away. Okay, so he will be right here. Okay, he's a half a mile away from the intersection. And he's traveling towards the intersection at a rate of 30 miles per hour. Okay, he spots a car traveling east past the intersection by a half of a mile. So the car's right about here, let's say. That's a half a mile. And the car's traveling that way. Okay, we don't know how fast though. It says the officer's radar device indicates that the car is traveling away from the officer at a speed of 20 miles an hour. Okay, so that means this distance here is growing at 20 miles an hour. Okay? How fast is the car going is our question. Alright, so how are we going to answer this? Let's start by drawing a diagram here. Well, there's already a diagram, but what I mean is, let's draw this rectangle here. Did I say rectangle? Sorry, I meant triangle. Okay, so there's a right triangle, right? And let's just label these sides A, B, and C. A and B will be the legs, and C will be the hypotenuse. Okay. What are we told? What are we told in the problem? We're told that A is a half of a mile. And we're told that B is a half of a mile. We're told that the officer is traveling towards the intersection at 30 miles an hour. So that tells us the rate of change of A. A is shrinking at 30 miles an hour, so its derivative is negative 30 miles per hour. And one more thing that we are told, the distance between the officer and the other car, which is the distance C, is growing at a rate of 20 miles per hour. So dc dt equals positive 20 miles per hour. That's everything that we are given. Okay? So how are we going to do this problem? Remember what I said in the last lecture. You write down the rates that are mentioned. Okay? So we are told the first rate we are told that the side of the triangle A is shrinking at 30 miles per hour. Okay. The second rate that is mentioned is the fact that C is growing at 20 miles an hour. So dc dt is positive 20 miles per hour. And the third rate that's mentioned is when they ask us how fast is the other car traveling, that means they are asking us to find the derivative of b. with respect to time. dB dt equals what? Okay? So that's the first thing we do, is we write down the rates that are mentioned. And then what's the second thing we do? We want a relationship between those quantities mentioned, which means relationship between A and B and C. Okay, what's the relationship? Well, it's a right triangle, so the relationship is A squared plus B squared equals C squared. Okay, and then what's the only thing we have to do? We differentiate that relationship implicitly with respect to t, plug in what we're given, solve for what we want. Okay, so what do I get when I take a squared plus b squared equals c squared? And I implicitly differentiate that with respect to t. We're going to get 2a times the derivative of a plus 2b times the derivative of b equals 2c times the derivative of c. Plug in what we're given. A is a half of a mile. The derivative of A is negative 30 miles per hour. B is a half of a mile. The derivative of B we don't know. C is how long is C? They didn't tell us, but certainly we could figure that out because we know the Pythagorean theorem. C squared equals A squared plus B squared. In fact, that's already written right there. So c squared is a fourth plus a fourth, which is a half. So that means c is the square root of a half. So that will be 1 over root 2 miles. And then finally, the derivative of c, we're told, is 20 miles per hour. Okay? If you want to use parentheses instead of those dots, that's fine. Okay, so what do we have here? That's negative 30. And what will the units be? Miles times miles per hour. That's going to be square miles per hour. Okay. What do we have here? That's going to be 1 mile times dB dt. And then we have our equal sign, and what do we have here? Two times 1 over root 2 is the square root of 2, so we're going to have 20 times the square root of 2 square miles per hour. All right, we're trying to find this guy right here. So let's add 30 square miles per hour to both sides, and we will end up with 1 mile times dB dt equals, and this is going to be 30 plus 20 root 2 square miles per hour. And then what? Divide both sides by 1 mile, and we'll get dB dt equals, okay, so 30 plus 20 root 2 divided by 1 is 30 plus 20 root 2, which is approximately 58.3. Here, let's write approximately. All right, 58.3, and then miles squared per hour divided by mile would be miles per hour. So that's how fast the car is going. About 58.3 miles per hour. So is the car going to get a speeding ticket? Yes, they are, because look, it's a 55-mile-an-hour zone, so they're speeding. Not very much, though. Maybe they won't get a ticket. It's only about 3 miles an hour over the speed limit. They'll probably get by without a ticket on that. But you see how to do the problem? It's just like the other ones. You write down the rates that are mentioned. You write down a relationship between the quantities in those rates. Implicitly differentiate, plug in what you're given, you find what you're asked for. Every related rate problem is basically the same thing over and over again. Okay, let's do one more. Okay, in this example, we have a video camera that's set up next to a road, 10 feet away, and it's going to record a car that's going to drive past at 100 miles an hour. Okay, as the car drives past, think about this. What's the camera going to have to do? The camera is going to have to rotate to record the car as it goes past, right? What we need to do is find the fastest rate that the camera will need to rotate. Okay? So, how are we going to do this problem? Let's draw a diagram again, and this time we're going to have a right triangle again. Okay, and this is 10 feet. And the car is going to be traveling this direction at 100 miles an hour. Here's what's different. We don't want to measure the rate of change of any of the sides of the triangle. This time we want to measure the rate of change of this angle. Let's call it theta. Okay? Let's call this side x and this side y. Okay? Now, let's solve this problem. So what's the first rate that's mentioned? The first rate that's mentioned is the speed of the car is 100 miles an hour. So that means the length x is changing. How fast? 100 miles an hour. And is x growing or shrinking? It is shrinking. So the derivative of x is negative 100 miles per hour. Okay? What is the second rate that's mentioned? It says what is the fastest rate the camera will need to rotate? So the second rate that is mentioned is d theta dt, and they want to know what that is. Okay? What are the units of that going to be? Well, we measure angles in radians. You could do degrees, but let's do radians. It make more sense. Per what? Well, I mean, you could, it's per time, right? Radians per time. So you could put hours. And that's fine. You can do the problem that way. But when you think about it, when you're rotating something like this, you're probably not going to measure the rotation in hours, right? Radians per hour is probably going to be more like seconds. You could do hours, but what if I said, please do the problem in radians per second? Okay? All right, good. And then what do I need to do? I need to find a relationship between the quantities involved, which are x and theta. Correct? All right. So, what is a relationship between x and theta? Well, if you know your trigonometry, then you know that one relationship is that the tangent of theta will equal x over 10, right? And then what do we do with that? We implicitly differentiate with respect to time. What's the derivative of tangent? It's secant squared, remember? So on the left, we're going to get secant squared theta times theta prime. And on the right, what's the derivative of x over 10? If you prefer, if it makes it easier for you, we can say 1/10 x. So what would the derivative be? It would be 1/10 times x prime. Okay, and then what do I do with that? I plug in what's given to me, and I find what I'm looking for. Okay, so what are we given? Well, we're only given one rate, which is dx dt is shrinking at a rate of 100 miles an hour. So for dx dt, we need to put negative 100 miles an hour. Okay, let me write this down. Negative 100 miles per hour. Now, what is that 10 right there measured in? That's 10 what? Is it 10 miles? No, the camera's not 10 miles away from the road. It's 10 feet. Now, this is another example of where the units are so important. And if you leave the units out, you're almost certain to get the problem wrong. Okay? Because by writing in the units, I see here that I have a mismatch of units. Look here, I have feet, and here I have miles. Those are both distances. So they're going to combine. In fact, a distance over a distance will cancel, right? But a foot doesn't cancel a mile. Those need to match up. in order for me to end up with the right number. So I either need to turn 10 feet into a certain number of miles, say how many miles is 10 feet, or I need to say how many feet is 100 miles. That second one is much easier. Okay, so I'm going to convert that negative 100 miles an hour, I'm going to convert that into a certain number of feet per hour. And how do you do that? Well, you have to know that there's 5,280 feet in a mile. Let me write this down. 1 mile equals 5,280 feet. Okay, so all I have to do is multiply by the fraction 5,280 feet over 1 mile, or that's not even a fraction really, because 5,280 over 1 is just 5,280. So that's 5,280 feet per mile. And now watch what happens. That feet cancels out with that feet. That mile cancels out with that mile. Works perfectly. Okay? And so what do we have here? We have secant squared theta times theta prime equals, okay, so we've got some numbers here. There's a 10 there, a negative 100 there, and a negative 5,280 there. And we need to multiply those together. So what are we going to end up with? We're going to end up with negative 52,800. Right? And what's the unit going to be on that? So look at the units. There's nothing else on top, right? All the units on the top canceled out, but there's still an hour on the bottom, right? So for right now, let's just put the units as this would be the proper way to do it, even though it's going to look very strange to you, but this is the proper way to do it. We just write 1 over hour. You might be asking 1 what? And the answer is 1 nothing. There is no units up there. Okay? But you have to write something. I can't do that. I have to put something there. So we put the number 1. Okay? All right, there we go. Now, trying to find d theta dt. Okay? So what do I need to do? I need to cancel out the secant squared theta, right? Remember that secant's 1 over cosine. So that's 1 over cosine squared. So how do I cancel that out? Multiply both sides by cosine squared. And here's going to be our answer for this part. D theta dt is going to equal negative 52,800 times cosine squared theta, and the units are 1 over hours. Okay? Now, here's something that I'm not sure if you have ever been told or not, but when you measure an angle, you can measure it in degrees or radians, right? Now, radians is often called a unitless measurement. So, when you're measuring an angle in radians and it comes out to be, let's just pick a number and say pi over 2, okay? You might say, here, let's write this down. This is what I'm trying to say. Suppose that you're measuring an angle theta, and it comes out to, what if it was 90 degrees? You would write 90 with a little symbol for degrees, right? Isn't that true? What if it was that size, but you were measuring in radians? That would be pi over 2, right? What's the symbol for radians? Well, there isn't one. Have you ever realized that? When you're measuring an angle in radians, there is no symbol that you write. Radians is what's called a unitless measurement. Okay, and up here, I could have said this earlier, but I just decided to wait. Up here in these units on the top, there is no units, right? The top is unitless, and radians are unitless. So that means if there's no units on the top and radians don't have units, then you can write radians on top. Let's do that. I think you'll find that that is going to work out nicely. We just write rads per hour or radians per hour. Okay? That's confusing sometimes. How can it have no units on a measurement? But that's hopefully that'll be okay with you. All right? So now we have d theta dt. The rate of change of the angle is this many radians per hour. Now I mentioned earlier, I said let's measure it in radians per second. That'll be nice. The number won't be so big. So how do you do that? Well, very similar to what we did changing miles into feet. Here we're going to change hours into seconds. 1 hour equals 3,600 seconds. Okay? So we just need to multiply times 1 hour for every 3,600 seconds. And what's going to happen, the hours are going to cancel out. And now we're going to have this much more manageable number. Negative 52,800 over 3,600. Still going to have cosine squared theta. And our units now are going to be radians per second. Okay? And 52,800 over 3,600 is 14 2/3. So that's negative 14 2/3 cosine squared theta radians per second. See, that number's a lot more manageable, right, than saying 52,800 radians per hour. Now the question says, let's just look here again. What is the fastest rate that the camera needs to rotate? Okay, so here's how fast the camera's rotating. Negative 14 2/3 radians per second times the cosine of this angle squared. What is the fastest that's going to be? Well, that's going to be the fastest when cosine theta is the largest. What's the largest cosine of theta can be? Cosine of theta is largest when it equals 1. When does cosine of theta equal 1? When theta is 0. So that means this camera will be rotating the fastest right when the car is passing the camera. And the camera is facing directly towards the road, so that this angle will then be theta at that point. Oh, sorry, I meant to say 0. So at that point in time, you would have cosine of theta equals 1. So the fastest the camera will ever rotate is it'll be rotating at 14 2/3, let's just say about 14.7 radians per second. Okay, why did I drop the negative sign? You don't have to, but the negative sign just tells me that the direction it's rotating is clockwise, right? Remember, we measure clockwise rotation as negative and counterclockwise as positive. So this negative sign right here is telling me that it is a clockwise rotation. That negative sign is not part of the telling me exactly the speed, it's telling me the direction. Just like this negative sign, which is not there, I should have put it here. Oh, I did, sorry. It's over here. Just like that negative sign right there is not telling me anything about the fact that the car is going 100 miles an hour. It's telling me that the car is traveling towards the camera. The negative sign on the derivative is just telling you direction. Okay? So that's a bit of a harder problem. I hope it makes sense. Some of them are a little bit harder like that. But the idea, though, is the same. You write down the first rate that's mentioned, the second rate that's mentioned. You write down the relationship between those quantities, and you differentiate and solve for what you're looking for.